Alright, so we want to figure out if the closures and interiors of connected sets are always connected. And so this is a little annoying because, first of all, they don't tell you what the correct answer is. You have to figure out for yourself. Thankfully, if you think about it intuitively, you should be able to come up with the correct solution. If you think about the closure of a set, if you've got a connected set and you take its closure, then you're typically only, in some sense, you're only adding in points that are like really close to your set. So it doesn't make sense that you could like take the closure of a set and get an entirely separate piece. And so, intuitively, it makes sense that the closure of a connected set should be connected. And that turns out to be proven that they're true, and that's what we'll prove. And as for interiors, we can actually look at subsets of R2 and come up with a pretty straightforward example. You can probably just think about it of a connected set whose interior is not connected. And one way of thinking about it is taking two separate connected sets and connecting them by like a line or a line segment, because line segments don't have any interior, so when you take the interior it goes away and you're left with the interiors of the two connected pieces that you started with. And as long as those interiors are not each empty, then you'll have a disconnected set. But anyways, so for closures, so let E be connected, and we want to prove that the closure of E is connected. So we want to write E closure as A union B, where A and B are separated, i.e. A closure intersect B equals A intersect B closure is the empty set. And now this argument is actually, it's sort of more of like a, I don't know, sort of more pushing around the symbols. It's not very like intuitively or at least visually obvious. There's a lot of things in like point set topology that I like to think about visually. This exercise does not seem to be one of them, but maybe there is. But anyway, so this is the proof that I'm giving it. The outline is based on something I found on Stack Exchange, actually. So what we're going to do is suppose that A is non-empty. I claim B is empty. And so if this is true, then okay, so we're not going to assume that A and B are separated. We're simply going to assume that these equations hold. And then what we're going to prove is that one of the two sets has to be empty, which means that A and B cannot be separated. And the lack of the fact that A and B cannot be separated for any choice of A and B such that A union B is the closure of E and they satisfy this equality, it guarantees that E closure must be connected. Because remember, in the definition of being separated, the two separated sets, the sets need to be non-empty. So these two sets whose union is E closure, we're going to prove that they can't be separated by proving that one of them has to be empty. Anyways, so since A is non-empty, there is some A in A. Now A intersect B closure is empty, which means that A complement, no. this means that A is contained in B closure complement. Right? Because no point of A is in B closure, and so every point of A is in the complement of B closure. So A is a subset of B closure complement. So since B closure complement is open, and that's because the closure of any set, we know that that's closed, and so you take the complement of a closed set and you get an open set. So B closure complement is open. There is an open neighborhood U of A contained in B closure complement. So A is lowercase a. I'm going to call this C instead, just so that I'm not using lowercase and uppercase a. So anyways, so C is contained in A, but it's also contained in this open set U. Now the fact that U is contained in B closure complement means that U intersected with B closure must be empty. And this implies U intersected with B is also empty, because B is a subset of B closure. So certainly if U does not intersect B closure, it can't intersect B. Alright. Now we know that C is in A, which is a subset of B closure. So C is a limit point of E. So it's a limit point of E, meaning that every neighborhood of C contains, every open neighborhood of C contains some element of E. But we know that U is an open neighborhood of C. So therefore U contains some element of E. So there is some element X which is in U, but which is also in E. And this is because of the fact that U is in fact an open neighborhood of C. Okay. So X is in U intersect E. So X cannot be in B because we know that X is in U. And the intersection of U and B is empty. So the fact that X is in U guarantees that it's not in B. And since X is in E, which is contained in E closure, which is precisely A union B, it must be the case that X is in A, because it's in E closure, and E closure is written as the disjoint union of A and B, so it's got to be in one of those two sets, and we know it's not in B, so it's in A. Okay, so we have X is in A. So X is in A, and it's also in E. So this tells us that E intersected with A is non-empty because it contains some element X. Alright. Note that we can write E as A intersect E union B intersect E. And now we're sort of getting to the point of, so we know that E is connected So if we're going to prove that E closure is connected, we must use the fact that E is connected. And here's how we're going to use it. We're actually going to take this E closure equals A union B, and then we're going to look at E equals A intersect E union B, union B intersect E. And so I guess like maybe if you were coming up with this proof on your own and not just sort of getting stuck and frustrated and looking up proofs on Math Stack Exchange, then what you would do is you'd probably start here and think, so we want to use the fact that E is connected, and all we have is that E closure equals A union B. So let's sort of use this to get some way of writing E in terms of A and B, and try to use the fact that E itself is connected. Okay, so this is the fact. This is the case. A intersect E and B intersect E are separated since A and B are. And this sort of makes sense intuitively. But let's just let's suppose that you didn't believe me and you wanted to prove this for yourself. Indeed, if you take A intersect E and take its union with B intersect E to prove that okay, so I guess what I want to say is A intersect B, A intersect E, and B intersect E. I'm not saying they're separated because we're going to prove that the second one is empty. But what we want to prove is that they also satisfy this condition of the closure of one intersected with the other is empty. So let's just jump straight to that. Or perhaps rather than, if we take the intersection or the closure of the first one and union with the second one, no, we want to take the intersection of these sets. So we're taking the closure of this thing, we're intersecting it with this thing. Now, if we remember exercise 7a, it tells us that you can distribute a closure over a finite intersection. So if you have so the closure of an intersection of finitely many sets is equal to the intersection of the closures of these sets. And that's the equality only holds in the case of in the finite case. For countable intersections or arbitrary intersections, I believe, the inclusion holds in one direction but not the other. And that was the point of exercise 7. But anyways, we can distribute this. This is A closure intersect E closure. And then if we remember how intersections work, intersections are associative. So we can just write this as A closure intersect E closure intersect B intersect E. And so then this is, we can group the A closure intersect B together, and then we have to intersect this with E intersect E closure, which is precisely going to be E. But now look, we know from our choice of A and B that A closure intersect B is empty, and so this is the empty set intersected with E, and so it's empty. And likewise, if we were to do it the other way, then we get the same result. B intersect E. You distribute out this becomes A intersect E intersect B closure intersect E closure, and so you can group the A intersect B closure together, then intersect this with E, and this will also be empty. Okay, so we know already that A intersect E, don't know why I flipped the letters, is non-empty. If it were the case that B intersect E is also non-empty, then E would not be connected, because then A intersect E and B intersect E would satisfy the conditions for being separated sets whose union is E. And so what this guarantees is that B intersect E is in fact empty. Okay, so B intersect E is empty. And we want to prove that all of B is empty. So all that remains is to prove that B intersected with E complement is empty. But then, so B, remember, E closure equals A intersected with, A union B. So B is a subset of E closure. So B is equal to B intersected with E closure. And here, there is actually another step that I will probably write out. Okay. Lastly, okay, so E is A intersect E union B intersect E. Well, E is a subset of E closure, which is A union B. And we know that B intersect E is empty. So E is a subset of A, which also implies that E closure is a subset of A closure. So then what we have is B. Again, going back to what I was doing before, we can indeed write it as B intersect E closure. But E closure is a subset of A closure, so this is a subset of B intersect A closure. But what do we know about this? One of our assumptions about A and B is that B intersect A closure is empty. So B is empty. Thus, E closure is connected, because if you write it as a union, if you write E closure as a union of two sets, which satisfy the union of two sets A and B such that A closure intersect B and A intersect B closure are both empty, then one of the two sets, either A or B, one of them has to be empty. Because if A is non-empty, then we've proven that B is empty, and if B is non-empty, then you can do this same argument with A and B reversed and prove that A is empty. And so since one of the sets needs to be empty, A and B cannot satisfy the definition of being separated sets, and so E closure cannot be written as the union of separated sets, and so it's connected. Alright. So that's this part. And yeah, again, it's a lot of just like a whole bunch of like none of the things that we've done here, like every step is sort of straightforward. Like all these set inclusions and stuff. Like, it's like, okay, obviously this is in this set, and this is in this set, and this is in this set. But actually coming up with, like, knowing that doing all of this will lead you to the proof, sort of, it's sort of not clear to me how this proof was developed in the first place. And maybe I'd be able to go to, like, give a more instructive proof if I knew, but alas, this is where we're at. It seems like you just, like, write down a whole bunch of things and write down a bunch of their obvious conclusions, and the answer just falls out. And perhaps the only thing I can think is, like, that insight that I gave earlier on writing E, trying to write E as a union of separated sets in terms of the A and B, whose union forms E closure, and sort of using the fact that E is connected in that way. But beyond that, I'm not super sure on how to come up with the proof in the first place, which sometimes is more difficult than understanding the proof itself. Well, in fact, there's a lot of cases where like a proof will define a function that just comes out of nowhere, and it just you use this function to prove the theorem, and you're like, okay, well, this leads us to a very short proof of the theorem that we're looking at, but I have no idea where you got this function from. And a lot of times that's the most difficult part of coming up with the proof in the first place, is figuring out where this thing came from. But anyways, might as well move on to the last part. And this part I have more of an issue with, because the first part, at least, like, we have all the tools necessary to prove it. This part we don't. So there's plenty of examples you can come up with. So for the last part, let E be, let's see, we're going to take all points x0 where x is between -1 and 1, and we're going to take the union with the closed ball of radius 1 centered at the point -2. Then we're going to take the union with the closed ball of radius 1 centered at +2. So what does this look like? So if this is the origin in R2, then we go to -1 and then 1, and then we've got 2 and then -2. Then we just got... not good at... Drawing circles is really hard. But yeah, you've sort of got this, like, barbell looking thing. Or maybe like some face which is very shocked or surprised looking at you. But anyways, this entire set is the set that we're considering. So if we look at the interior of E, this is going to be the open ball of radius 1 centered at -2 union the open ball of radius 1 centered at 2, which is disconnected. And then, let's see here, so it's disconnected because we need to find two sets A and B. Well, you just let A be the ball of radius 1 centered at -2, and you let B be the ball of radius 1 centered at 2, and then you can easily prove that this is disconnected. E itself is connected, but we don't have the tools to prove it, which is why I don't like this part of the problem. this is one of those things, it's very, if you look at this, it's very easy to see, or it should be intuitive to see that, like, this should be a connected set, because there's no, like, gaps at all in this. This is a compact set, everything's, totally, yeah, it should be all connected. But if you actually what you have to do, if you want to prove that this is connected, you have to take any arbitrary set A and B or you have to prove that there are no two separated sets A and B whose union is E. By the way, E0 is the interior of E. But yeah, so for general sets A and B, there's no real straightforward way to prove that. You need to have some other properties. Like in the previous part of this exercise, we were actually able to prove something because we knew things about E and E closure, and we were able to use actual topological properties. It was still sort of tricky, and there were a lot of details, but we were able to prove it. But here we have this specific set, but we don't really know. We don't have the tools to describe its properties topologically, and that's what you would really need in order to prove that this is disconnected. Now, one thing that we could prove is, I was looking into this a little bit. Let's see here. There's a lot of like point set topology textbooks where they define connectedness by saying a set E is connected if you can write E as a union of A and B, where A and B are disjoint and non-empty, but also open sets, rather than arbitrary sets where the closure of one does not intersect the other. And I don't like that definition, and that's the definition that Rudin has used, and I don't really like it because it uses, I mean, it's more general because you can use arbitrary sets A and B rather than just open sets, but you can't really, there's much less to work with. Whereas, because with arbitrary sets A and B, there's not much you can say about them, because sets can look really, really, really weird. Which is sort of, starts to become clear when you start thinking about things like just the nuances of the rationals and the irrationals. Also, we looked at the Cantor set in this section, but sets start to look even weirder when you move on to measure theory, and you start to realize, like, sets in general, just there's not much you can say about them. But if we use this open definition, it would not be super difficult, because if you have open sets A and B, then you would need to have, if you take, like, for example, the set A, and you consider its boundary, so the basic idea here is, let's say you have, like, A looks like this, and here I've drawn it with like a line, but imagine that this is an open set, and so this dark line that I've drawn here, or this dark curve, is actually the boundary of A, and it's really everything on the inside which comprises the set A itself. And so what you have to do is you have to then look at the boundary here, the boundary of A which intersects E, and if you look at the points on that boundary, the points on that boundary need to be in either A or B. And they're not in A because A does not contain any of its boundary points because it's open. So all the points on this boundary here must be in... Oh, did not want to do that. I have to go do this. So all the points on this boundary here need to belong to B. And so B then has to look something like this, maybe. But then we see that we have this intersection here of A and B. because B needs to contain these boundary values. And if B did not intersect A, then you would have points in B along, well, yeah, you've got points in B along this boundary. You take any neighborhood and it has to be entirely contained in B. However, because it's part of the boundary of A, any neighborhood of a point on this boundary contains points in A. So therefore it contains points in both B and A. And so therefore it's not possible to do this. So I think there is a way to prove it. So let me just write that out. I mean, we're essentially done with the exercise. I don't think, like, if you're getting graded on this, I don't think they'd expect you to prove that that this set here is connected. And in fact, there's no real good examples I can think of that you can use, or any other examples that you could come up with of a set E whose interior is disconnected, but which itself is connected, and which you're able to prove that it's connected. What you'd have to do is you might be able to, I think the best you could do is maybe you can prove that if you take a direct product of connected sets, then you get a connected set. So we proved in this textbook that line segments are connected, and that's great, but that doesn't tell you anything about R2. But if you know that direct products of connected sets are connected, then what you can do is you can go ahead and just take the direct product of two line segments, and then you have a rectangle, and so then you know that rectangles are connected in R2. But then you still need to sort of glue two rectangles together using a line segment. It's not clear what you would do to prove that. You might have to use like path connectedness or something, or understand the nuance or the differences between connectedness in this definition and also the definition of path connectedness. But anyways, if E is connected, let's get back to this, when E equals A union B, so if E is disconnected when there exists A and B, disjoint, non-empty, and open, such that E equals A union B, then if such A and B exist for E as above, the boundary of A intersected with E would have to be non-empty. And I think this itself this fact itself, I think, would actually be tricky to prove, because this is really what we're using here. So this means that the boundary of A intersected with E is a subset of B. So B cannot be open because any neighborhood of any point in this set contains points in A by the definition of the boundary of A. And of course, oh, I should say that. So the boundary of A is the closure of A and you remove the interior of A. It's an important point. And again, I don't know if this is even something we've talked about. But anyways, the point here is that there should be ways to prove that this set E is disconnected, or to prove that this set E is connected, but we don't have those tools. It's much easier to prove that something is disconnected than to prove that it's connected. And so for this exercise, because we are nowhere near knowledgeable enough, or we have nowhere near the tools necessary to prove that the set E is connected, I don't think they are looking for a proof. I think they're just looking for an example that you can point to and say like, oh, well, intuitively this looks like something which is connected. But yeah, so the point is, you take a closure of connected sets are connected, interiors of connected sets can be disconnected. And that is the point of this exercise, and so now we are done.